You are still able to hear me, Anke?
Yes, yes, yes.
Okay, let me try to write something. Are you able to see what I'm writing?
No.
Ah, okay. Okay, no
Wait,
problem.
wait, I see. Write something, write something.
Oh, you're not able to see?
Nah. Yeah, what's going on? Maybe the color you're using. I see your thing is moving. I see the movements, but I don't see the writing.
Oh, no, no problem. No, I understand why. I think I know why. Are you able to see?
Yes.
Okay. Galvanic cells, right. So, here in this part of chemistry, remember we're doing it's electrochemistry, right? And in this part
Yeah.
of chemistry, we're dealing with the interaction between chemical reactions
Mm-hmm.
and electricity. And then if we can understand what is electricity, electricity is essentially current flow. Once you have current that is flowing, then you have electricity. Sorry. So, um, so in that is what is happening now. In particular, in galvanic cell, we are talking about the conversion of chemical reactions to no chemical energy from chemical reactions, right? So we can write it as chemical energy. We're converting it to electrical energy. So this is the energy conversion in a galvanic cell, chemical energy to electrical energy. And essentially, this is happening to, like, we're kind of like zooming into a cell just to see how a cell actually looks like inside.
I thought like a battery somewhere happened, but you said chemical reactions to electricity. So could you
Mm-hmm.
like I don't know, can you further explain that?
The reactions we are going to look at them, they are redox reactions.
Mm-hmm. And those redox reactions are used for electricity.
Once they take place, right, something is happening that is going to cause electricity.
Oh, okay.
Yeah, so that's what we're going to explore in just a second. To say that they are like this, right? We can take one beaker, then you take another one, and then you can put a solution there, right? You just say you put in there um, a solution. Now, this solution we're going to talk about what is it like, what solution do we use. We take a solution there, and then we're going to take metal strips, ne? Metal strips. In terms of metal strips, what am I saying? If you have a sheet of a metal, right? If you cut it, or you can make a rod out of it, like, make a small roll which is like a cylinder like oven, then
Mm-hmm.
this would be a rod. But if you cut it, a piece of it like this, and it is flat, that will be a strip of that metal, you see. These are what we use as electrodes. We call them electrodes. So electrode is essentially when you take a metal, you cut it, and then you make your electrode, or you make a roll out of it. You understand me?
Electrodes are like what you cut, the metal you cut.
Yeah, yeah. You know a metal, right? Like,
Yeah.
examples could be, I don't know, in Sesotho, as we call it masenge. You have never seen masenge.
Hey, Stinson, I'm uncultured. I think you should know this.
Yo, 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 yo. Ma'am, You know, physics sometimes needs people who go to the ground and play with the dust. Yeah? But then, to make you try and understand, you can think of your, a spoon that you are using, which is made up of steel, stainless steel spoon. Eh?
Yeah.
Right, yeah. If you were to cut that spoon there, you can actually use this as what we call an electrode.
Okay.
Yeah, it's just a piece of metal. Ne?
Piece of metal, yes.
Yes. So here you are, you take your rod here or your strip, you put it here, and then you take another one, you put it there. Now let's just say this one it's a copper metal, and then let's say this one is a zinc metal. Okay? Right. Once you put them in the solution, your solution should resonate with the type of electrode you have. What I mean is that if you have a copper metal, make sure that the solution you're going to put in this beaker, that solution should be at least maybe copper sulfate. Or what?
Oh, so it must be similar in terms of material.
Yes. It could be copper sulfate, it could be copper nitrate, as long as it has copper. Or what?
Yeah.
By the way, sulfate is SO4 2 minus, and then nitrate is NO3 minus. Okay?
Yes.
Now, if I put copper 2 plus, because that is the one that we mostly use, it means you have 2 plus there. I get it. So remember, when you are naming compounds in grade 10, we said that this would be just CuSO4. Okay? If you have Cu2 plus and then this one is 1, remember the 1 goes here, the 2 goes there.
Then you put the thing in brackets, NO3 in brackets.
Perfect. I'm so glad that at least you are aware of this, because now that comes into play when you have to name the what, when you have to name those compounds or the solution you put there. Okay.
Yeah.
Perfect. So here we're going to have zinc. We're going to have zinc sulfate also. Now, actually, they do have some colors, right? We don't really focus much on the color of the solution because copper sulfate, I think it's like a bluish solution, and I think zinc is it colorless, something like that.
Yeah.
Yeah, but the main point is that your metal should be linking with the type of solution you have inside the beaker. Then now, after that, we then say, okay, now that we have our copper and the zinc, we are going to join them. Or what?
Join them, yes.
We join them. We can use a wire, a conductor on top. Same as what you would use in an electrical cell. Or what?
Yeah.
Perfect. So here we are. We can even put a light bulb here for illustration purposes. Say this is a light bulb, and then we connect it to that side. The moment we do this, two things are going to happen. We're going to have a loss of electrons from one of the metals, and then we're also going to have a gain of electrons from one of the metals. Okay, now the question would be, which one will lose electrons, which one will gain electrons? Okay.
Yeah.
Perfect. So in order for us to do that, or rather to get the answer to that, we're going to use table 4b. You remember table 4b? Table 4b. Let me take one of the previous papers here in paper 2.
Oh, you mean that long table? Stop using fancy words, bro. You're tricking me up.
Can't you what? What do we call it?
I'm thinking it's some complex thing. You can
But that is the one, Amos. Yeah.
Yeah, call it the table that shows oxidation and reduction.
But Remember, Kiri, there are two of them. There is 4A, there is
Yeah, there's
4B.
4A and 4B, yeah.
Aha. So I'm glad I actually found a paper that has a smaller version of it. Let me put it here. So this is what I'm
What's
referring to.
Oh, okay, okay. I was gonna say, make sure it's not fake.
It's very nice in this one. You see it?
Mm.
Yeah, this should be 4B if I'm not mistaken, because 4B, let me confirm it first.
No,
Because,
it's not 4B.
are you sure?
Yeah, I have it in front of me as well.
It's not 4B.
No.
Zinc, okay, 4B. Zinc is on top, copper is on the bottom. The way to confirm zinc is on top. No, it is the one. Open. It just that they cut it, they took a portion of it. Open.
Mm.
Yes. Now on this table 4B, what you would do then is that since we're talking about copper and zinc, ne, you are going to go to copper and zinc. Zinc is here, right?
Okay.
You circle the left and the right, and then copper. The copper that we use, remember there is copper that has plus here, there's copper that has nothing here, right?
Mm-hmm.
And then there's also this other copper that has, that is copper plus. The one that we use in most cases 100% of the time is this one here. Okay.
The one that has nothing.
But it should be copper 2 plus, not copper plus. Or what? That is that is the one we use. Right. So because you are not allowed to do this on your exam paper, right? You are not allowed. So what you do is that you can still do what I did. However, you're going to do it on your own answer sheet where you will be answering. Wabon. To avoid any problems out there. You don't want to say, but I said you should do it and stuff. No. We're gonna look at how to do it. So in terms of how you can do it, you can just simply write it down, right? The one on top is zinc 2 plus, and then you have plus 2 electrons, and then you have zinc.
So you copy it as it is on the table.
But focusing on the 2 that you are interested in. Wabon. Yeah, you neglect the rest, and then you write those ones that you're focusing on, because those are our electrodes there. So now that we have these, right, you can then, after that, you remember my name. My name is Clayton. Oh yes, I sometimes forget it, but then it's fine. Do not forget me, because you're going to start from the top, and then you're gonna draw write C as if you're going to write lighting, to remember me when you are writing. Now the arrow is yeah, and the arrow is starting here. And then when you write my name, you do this first. Yeah, I don't write my name like this. No. Actually, if you do that, it's not my name. The C must start from here. If you write it like this, it's not C. You understand me? Right. So now what happens there? I need you to know that on top, it's always the one on top. Since we're talking about galvanic cells, the one on top is always oxidation. And then the one on the bottom is always reduction.
So my question is, right, I'm in the exam venue, they're giving me the scenario you give me, right? What if I start with copper, then I go with zinc? Will the oxidation and reduction thing still apply? Or do I have to go according to how in the 4B table it is that they start with zinc, then they go to copper?
So you're saying if you do it like this?
So what if I started with copper? Yes. No, like...
You said copper on top.
Yeah, what if I start, let's say I know, okay, Clayton said that I must look at these two on the 4B. So I go to the 4B table. Then instead of starting with zinc, I start with copper. With the oxidation and reduction things still apply, even though they're in two different positions.
Well, if you do it like this now, it becomes the opposite, because now the one that was on the bottom, you put it on top. So now it's the opposite. To say on top, it should be reduction. On the bottom, it should be oxidation. And you are no longer going to start from top to bottom, but you are now going to start from the bottom to the top. Now you write the C like this.
Okay. So I'm saying, should we go according to how the table has placed them? Because it starts off with zinc, then it goes to copper.
Please, please, if you can do that, you are always on the safe side, ne?
Okay.
Great. So now that we have this, right, then this allows us to write our oxidation reaction, to say, oh, okay, our oxidation will be, you follow exactly the way it is. You start with zinc, and you write it, followed by an arrow, right? But the arrow, make sure it's not double arrowed, it's just one arrow, ne?
Yes.
Then here you are going to copy it exactly the way it is. We're just going to write zinc 2 plus 2 electrons. Then you are done with the oxidation reaction. Then you go to the reduction reaction, ne? So on the reduction reaction, remember, Kira, we are going in this way, following that, ne? So we started with zinc, we went to the arrow, we wrote the zinc 2 plus. Now we are going to start with copper 2 plus, isn't it?
Yeah.
Copper 2 plus, and then we go to the 2 electrons, and get one arrow, and then we finish with copper, and get perfect. So now this is the reduction. Then you are okay. The main key in galvanic cells is to identify the oxidation and the reduction reaction. After that, everything is very easy. Eh? Now we're going to find what you call wait, before we can even find the net, what does oxidation mean? What does reduction mean?
Isn't oxidation the the gain in electron, the loss in electrons?
So we say oil, and then what? Rig. Anger. Oil rig assist us to remember that. To say oxidation is loss, right? Oxidation is loss, and then reduction is gain of electrons. So that means that something that is undergoing reduction, it is gaining electrons. Something that is undergoing oxidation, it is losing electrons, ne? Perfect. So we can see from the reactions that zinc undergoes oxidation, and then copper 2 plus undergoes reduction, meaning it is reduced. So we then go back here and say, oh, we said zinc is going to undergo oxidation. So it means here on zinc, we know that oxidation will be taking place. And then on copper, reduction will be taking place. That means that since this thing here is going to be losing electrons, what is going to happen is that over time the mass of that electrode is going to be decreasing. To say the mass over time is gonna be like this. Someone said it is being chowed. I think it makes better sense to say zinc is being chowed. There you can see it's being eaten away, and because every time it is losing electrons, and then it's becoming zinc 2 plus in the solution. Okay, it's becoming zinc 2 plus in the solution.
Does that mean the copper becomes bigger, or does it stay the same?
The copper, it means it's becoming bigger. The copper will be becoming bigger, because the electrons that are lost by this one, where do they go? They flow through the they flow through the circuit, right? And then they go to copper, and and then the copper 2 plus, remember 2 plus means you are shorting electrons. Plus means you are shorting electrons. So
let me just, sorry.
yes.
No, continue.
Right. So here the copper 2 plus is receiving those electrons that are coming from the zinc, and then now they increase the mass of this electrode of copper. Angel. So this is reduction, gaining of those electrons. That side is oxidation. Right. And then now, so as you can see, there is a flow of electrons. For the fact that there is flow of electrons, those electrons, remember, once they pass through the light bulb takes some of the energy of those electrons and then it converts it to electrical energy, to light energy. Do you see that? So that is why we say a chemical reaction, which were the oxidation reactions, they have caused electricity. So we have converted chemical energy to electrical energy. Is it clear?
Chemical energy to electrical energy.
Yes, from the chemical reactions that occurred there. Wabon. And which ones are those? The oxidation reaction, which means the loss of electrons of zinc, and then the reduction reaction, which means the gain of electrons of the copper. It has caused electricity. Thank you.
Yeah.
Right, yes, that is the whole idea behind galvanic cells. To just say that the other one undergoes oxidation, the other one undergoes reduction. It's always like that. The other one undergoes oxidation, the other one reduction. The rest, you know what is the rest? The rest is to now name these electrodes, give them some polarity and stuff. But the main idea, the main concept lies here, to say the other one is losing, the other one is gaining, and then we have electricity. This is how your cell works. You know, a battery, ne? That's how your battery, your battery, wabon. That's how it works. Inside there are chemical reactions that are occurring, and then those chemical reactions, they cause the electrons to flow in a circuit. If you can still remember when we were doing electric circuits, do you still remember us saying that the electrons are flowing in there, and as they are flowing in the circuit, they're delivering energy to the resistors? You remember?
Yeah.
Those electrons that flow there, it's because of the reactions that occurred inside. That is what is causing the electrons to flow. Are we clear?
Yeah.
Right. That is how you link the chemistry part to the physics part. Now, there is a very, very important component we need in order for this thing to be sustained. Because let's understand the following. If this thing can go on, we are going to have what we call a buildup of charge. So to prevent a buildup of charge, we usually use what we call a salt bridge. Ne? So we use what we call a salt bridge. We connect it here like this. Right. They usually like to ask, what is that component there? So this is our salt bridge. Now, in terms of the salt bridge,
what was the purpose of the salt bridge?
So what is the purpose of the salt bridge? Very, very nice question. It has two main functions, ne? So the first one, number one, is that it completes the circuit. I like it because it's so short. It completes the circuit. And then the next one is to say that salt bridge there, it prevents build-up of charge. Prevents build up of charge. Right, that is it there. you must understand that the salt bridge is going to have some solution in there. Usually they like to put sodium chloride because it's a salt bridge, but it does not mean it is always sodium chloride. They can even put potassium chloride, they can put magnesium chloride, right? As long as there are some ions in that salt bridge. Those ions, they just make sure that the circuit is complete, and also they prevent the buildup of charge in both beakers that we're using.
So if when they mean buildup of charge, can you please explain that a bit further? Does it mean like it blocks the electrons from passing? If I'm saying that right.
Very nice question too. Hey, well, now you want us to go deeper, of which it's okay, right?
I just want to understand. I'm so sorry.
No,
I
no.
think that we did this section quite quickly, so I'm quite confused on why certain things happen.
Right, no problem, no problem. So remember that we said the zinc is losing electrons, right?
Yeah, yeah.
Right. So if I can put a small atom of zinc here so that you can understand how what is happening, I'll just show the two electrons here, ne? To say,
Yeah.
as the zinc is losing electrons, it starts from zinc. I get from the reaction itself. We said it starts from zinc, which was the metal.
Mm-hmm.
It loses two electrons, it becomes zinc 2 plus, which means now it has lost electrons. I get perfect. Now, immediately it loses electrons, it goes inside the solution as zinc 2 plus. You understand me? Now now imagine that this is occurring for a long period of time. It means you'll be forming zinc 2 plus, you'll be forming zinc 2 plus. Do you see that this whole beaker will end up being positively charged? Okay. Once the whole beaker becomes positively charged, do you still remember that the electrons were flowing to that side, to copper? But once it can become positively charged, remember the electrons are negatively charged. Are they not going to be attracted back?
They will be adjusted.
Aha. So we have to prevent that. We have to prevent this whole beaker from being positively charged alone. So what do? The salt bridge, the salt bridge has a positive ion which will be Na plus and some negative ions which is Cl minus, ne?
Yeah.
What the salt bridge will do is that it will send the negative ions into this one, the negative ions into this one, like Cl minus. You see,
Yeah.
that Cl minus neutralizes the positives,
Oh, yeah.
to make sure that this side becomes neutral. Similar thing is going to be occurring this side. This side they are sending the positive ones. Do you understand it? Yeah, so that is why we say that it prevents buildup of charge. It prevents one beaker from being completely positive and the other beaker being completely negative by maintaining electrical neutrality. But to put it easily, we prevent buildup of charge. Yes. So that is what is happening there. So if you can just remember the functions of a salt bridge, to say it completes the circuit and it prevents buildup of charge. If you can remember for me how to find the oxidation reaction and the reduction reaction using the method that we told you, table 4b, ne? Then you should definitely be okay. Now, the next thing we need to know also, right, is that now that we know how to find the oxidation and reduction, you need to know how to get the net reaction. I get it.
Yes.
Now, getting the net reaction, we already did it in grade 11. Do you still remember?
Yes.
Yes, we did it in grade 11 when we were discussing redox reactions. So it does not change. We are still going to say you take everything that is on the left hand side of the arrows, ne? You write it zinc plus copper 2 plus 2 electrons forms. Then you take everything on the right side of the arrows to say zinc 2 plus 2 electrons plus copper. And here,
Can you please explain that again? How do you take it? You take everything from the left side. Oh yes, I see.
We take everything from the left, zinc, copper 2 plus and 2 electrons. Then we write the arrow, and then we take everything on the right side. Right, then we will have that. Then after that, remember that this will cancel that. Therefore, the net reaction will be zinc plus copper 2 plus. Now we must also try to show the phases. Remember, zinc starts with as solid. Once you have 2 plus, I want you to remember that it will be in aqueous solution all the time. Ne?
For copper.
No, anything that has plus, that has minus is going to be aqueous solution, okay? Even zinc 2 plus here is going to be aqueous solution. Because remember,
It has a minus.
yes, even when it has a minus, like when you have NO3 minus, it is in aqueous, because remember, these are ions and they are flowing inside the solution. One thought. They are inside the solution. So if you can look at it in terms of here, we're saying zinc starts off as a solid. It loses electrons and becomes zinc 2 plus, which will go inside the solution. That's why we put AQ on it. Yes, so you must know ions, they're going to be in aqueous.
Does it mean ones that have nothing, like have one, does it become a solid?
Yeah, if it is 1, it is 0. Remember, it's 0 when it is neutral. Like if it's 0, it's a solid. It's a solid. For example, you see this Ag, you see that copper, you see that iron, you see that chromium, zinc, chromium, ne? You would put solid there. Then the rest with plus, minus and stuff, you put aqueous solution. Yeah, that's how it works. So this is the net reaction. From the net reaction, right, another thing that they can now ask you is to say, can you tell us from there which one is the, okay, maybe before that, which one is the reducing agent? Right, they will ask you which one is the reducing agent, and then which one is the oxidizing agent. Now, which one would you say is the reducing agent?
You said reduce. Oh, that's just English. It's the one that gains electrons, right?
No, now remember, that one we said reduction. Reduction is a process, or what is a process whereby electrons are gained. Oxidation is a process whereby electrons are lost. However, when you talk about the agents will be these ones here, these ones here. It will be so usually they're the ones on the, like, that are starting. When you wrote your oxidation and reduction correctly, the first ones are always the agents. Now in terms of those, there is an oxidizing agent, there is reducing. Now to remember this, right, a reducing agent undergoes oxidation, ne? And then an oxidizing agent undergoes reduction. It's always the opposite in terms of agents. Now let's look at the reaction here. Which one undergoes oxidation?
Looking at the net reaction.
No, looking at these two reactions that we had here.
Okay.
Check them.
The one that undergoes reduction, right? Could you say it's the two? The zinc.
The zinc undergoes oxidation, ne? So that is.
It goes from being neutral to having 2 plus.
So that is your reducing agent, okay? And then the one that undergoes the reduction is called your oxidizing agent. So it will be Cu2 plus. All right. So let's just remember that. Okay. Reducing agent undergoes oxidation. Oxidizing agent undergoes reduction. Because they're always the opposite.
Yeah,
Right. And then the last thing, or the two last things we need to know about galvanic cells. It's quite a theory based chapter. I don't really like theory. However, if I understand theory, I'm able to remember it. You see,
yeah. How did you pass life science?
like I told you, if I am able to understand what you are telling me in terms of life science, to say this is what is happening in your body, if I'm able to understand it, I will remember the theory. Or what?
Yeah,
But if it's just theory reading and then it has no practical meaning, and like, it gets too much, like, reading history, I wouldn't be able to do that. What?
how do you know that?
I've tried before in social science, it didn't end well. Okay, so the next thing we need to know is to get what we call a cell notation. What?
Mm-hmm.
Right. A cell notation, this one is simply as follows, right? Mina, the way I write it is this one. I go to check the oxidation reaction. Our oxidation reaction is this one. I get
Yes.
perfect. This is what you're going to simply do. Ignore the electrons. You just have to do this. You just have to do this. Then that is your cell notation. What am I saying? You are just going to write zinc first, and please include the phases. Remember, we said it's neutral, so it means
Solid.
solid. And then zinc 2 plus, you write it.
Accurate.
It's aqueous. Do you agree that these are two different phases?
Yes.
So we use this line to separate them, okay?
Yes.
We call this line, if they ask you, we call it a phase boundary. So a phase boundary separates the two different phases. Now remember, after saying zinc and zinc 2 plus, you have the salt bridge, right? Before we can go to copper. That is why after that we then say we have a salt bridge, which is represented by the two lines there. Right. And then we say we go to a copper. Remember I said ignore the electrons. Now you're going to write this one first to say Cu2 plus, put aqueous there, and then copper solid. Then that will be your cell notation. You just have to go to the oxidation reaction. If we can remember that for me, to say we go to the oxidation reaction, we just take the first component and the second component. You go to the reduction reaction, you take the first component and the second component. Then you are done.
So oxidation must always be the first one.
Okay, very nice. So it means the first part is always the oxidation here. It's always the oxidation. Then the second part is always the reduction. And knowing that, remember that since we are saying that this is oxidation, it means zinc went through oxidation. That is why usually they say to you, when you are writing a cell notation, you must write the reducing agent and then put the oxidized species. They say the oxidized species, and then they say write the oxidizing agent and then write the reduced species. But hey, I feel like with these terminology and stuff, hey, it's a bit difficult to remember that I must
Not like science. Species group. No, no.
not species.
I already deleted life science.
Well, so I try my best to avoid that by just saying, okay, sharp, it's fine. We know that a reducing agent undergoes oxidation, and that's what you must write first. So when I just go to the oxidation reaction, get the first component and the second one, go to the reduction, get the first component and the second one, then you are done. Okay. Right, so that is how we do that then. Now, after cell notation, right, the last thing, the last thing is what we call the cell potential, or what? Cell potential. Are you still there?
Good question. Yeah.
Mm-hmm. Oh
I'm
yeah,
gonna
yeah.
do an exercise because I'd like to do an exercise and see how it's done.
With this time I have limited time. You know what? It's fine. Let's actually try to see a bit of an exercise, or what, before we can go to this one. But this was like the last part of it. If maybe I can just write it to say,
Yeah.
here, what we are doing is that now we are calculating the EMF produced. Remember, we said we are producing electricity, so we're calculating the
Yeah.
EMF produced, and then to get it, you say E naught of reduction. Yo, how is that for me? I keep forgetting it. Is what? Oh, E cell, E naught cell, okay. E naught cell is equal to E naught of I like to write reduction minus oxidation. I like the one of reduction minus oxidation. Perfect. So now, how do we actually deal with this? We just go to the reduction reaction on our table 4b. Remember, we said the one that went through reduction is copper, is this one. And get
Yes.
the E naught of that is plus 0.34. Do you see it?
Yes.
That's the one you write there. And then you say minus, you go to the one for oxidation, which is zinc, right? And then the E naught there is minus 0.76. You write it minus 0.76. So your answer.
Question. I'm
Yeah.
so sorry.
No
But
stress.
remember we remember for the we decided which one was going through oxidation, which one was going through reduction.
Yeah.
We used the 4B table. We said the first one was zinc because it was at the top. We said it was going through oxidation.
Mm-hmm.
And we said copper was the one going reduction. It's always like that from top to bottom when you're taking like maybe two. The toppest one goes through oxidation. And the second, the one at the bottom goes through reduction. Is it always like that?
It's always like that.
Okay.
It's always yeah.
So if maybe we were doing copper and Cl, and then would copper be the one going through oxidation, then Cl would be going through reduction, right?
That's it. Yes.
Okay. I get it.
Right.
Just making sure.
No problem. Perfect. And then from there, now that you would know which one is a reduction, you just go and take its value there, you plug it in. Oxidation, you take its value, you plug it in, then you solve for this.
Yeah.
And for galvanic cells, you must always get the answer as positive. If you get it as negative, know that you did something wrong. You probably mixed up the oxidation and the reduction, okay?
So the cell potential must always be positive.
Yes, because these reactions are called spontaneous reactions. They actually naturally occur once we connect them. Yeah, electrolysis, you get the cell potential as negative.
Yeah.
Alright, so that is all about galvanic cell. That is like the full information about galvanic cell. If you know that, definitely you are going to be okay. Apart from also, lastly, it's a lot of things. Lastly, you must know that in terms of the cathode and the anode, because we have two, remember that we have two electrodes, Anger? You have two electrodes. So the other one should be the anode, the other one should be the cathode. Now, the cathode is positive. Cathode is the positively charged one, and then the anode is the negatively charged one. just as when you have a battery, right? Remember, when you have a battery, it has a negative side and a positive side. Since this is our cell, we should have a positive and a negative. So how do we know where is the cathode? Well, where reduction is occurring, that's where you're going to find the cathode. Ne? For you to remember that, you can just say red cat. It will remind you that where there is reduction is the cathode. And then where is oxidation, right? Where oxidation is occurring, this will be your anode. Now this should mean that then this is positively charged and then this is negatively charged in terms of your electrodes, and then you would be done with that. Ooh, then you would be done with that. Okay, yeah, so then you would be done with that. And then yeah, cathode, remember, is positive, anode is negative. If you want to remember also that there's someone who said you can actually say guns guns can protect a nation, right? Guns can protect a nation, which means in galvanic cell, the cathode is positively charged, the cathode is positively charged, then the anode will be negatively charged. That is it there. Are we clear? Right. Right, so that is it there, and then you can try to attempt some questions, right?